And next speaker is Rudy Grimm from the University of Innsbruck that will tell us about Efimov physics.
So my remote control got stuck somehow. I think I get it out. Yes. Okay. Okay. So welcome everybody. I think we're all having a great time here. It will be a great week. Thanks to Trey and Gretchen for organizing this. It's wonderful, and thanks for organizing thanks for inviting me to come here. And so my story is about new developments in few body physics with ultracold atoms. And the name that you will hear very often is this one, Efimov or Efimov, how the Russians say. But just to give you a very simple and elementary introduction and what I'm going to talk about, let me consider this slide. So this is my simple model of an ultracold gas, a few particles. Sometimes they collide. But I mean, we are interested in using quantum mechanics to increase the interaction and to use a resonance phenomenon, the Feshbach-resonance, just by changing the magnetic field to go to very large values of the scattering length. And then, I mean, the interaction, the cross-section gets much larger. You know, it's characterized by the S-wave scattering length. And then you find increasing situations where they collide much more often. But you find also situations where three get closely together. Here 3 and even 4 and even more ones. So these are then few body states. And so we are interested in the field of few body physics with ultracold atoms, how these few body physics affects then the behavior of the whole system. So here we don't think about the shape of the container and so on. We don't have any lattices. It's just a huge volume gas, an essentially free gas of atoms. So the paradigm of the field of few body physics dates back to 1970, and this is the original drawing of Efimov's scenario in the Russian nuclear physics journal. I think Efimov at that time, he didn't have cold atoms in mind. That was a little bit too early, but of course he was considering few nucleon systems. So this is something that comes from nuclear physics. And what is plotted here is that's as a function of 1 over A. So that's here the point where the scattering length diverges, the energy, or better say the square root of the energy, K, here. And what he found is that then if the scattering length is very large, he found a universal series of trimer states. These are very weakly bound trimer states. They look like this here. They form an infinite ladder, and the infinite ladder is characterized by a discrete scaling factor of 22.7. So if you have one state like this, you find the next one, which is just looks, it's the same shape, but it's 22.7 times bigger. And the next one is even much larger. So it's a huge number, this 22.7. And where does this come from, this discrete scaling? Actually, the very simple picture, if you express it in the right coordinate system, hyperspherical coordinates, then actually this problem of these contact interaction between pairs of atoms, this leads then to an effective 1 over r squared potential, minus 1 over r squared potential here. And this potential then has this discrete scaling solution. Here I plotted the energy state, a geometric series with a factor of 2. Well, it's in reality, it's a factor of 22.7 squared, 515. But it's not very good to illustrate this. So this is a geometric spectrum. And we are looking for these states. So, but how can we observe them? What is our possibility to see these extremely weakly bound states? And resonance phenomena are very important here. Resonance phenomena, here, for example, when an Efimov state crosses the threshold, here the second one crosses the threshold, and then actually, so 3 free atoms colliding at very, very low energy, they couple to this three-body trimer state. But now, in the ultracold atom world, and this is not what Efimov had in mind, but in the ultracold atom world, there are many more deeply bound states below here. So these can be deeply bound dimers and atoms, many, many states. And what happens then is that the Efimov state can decay into a deeply bound dimer-free atom. And this is essentially what it means, that there's an efficient pathway for three-body recombination. So what you expect is a strongly enhanced three-body recombination. Similar things happen on the other side, the atom-dimer resonances, but I don't want to talk about this here. A three-body recombination resonance would be the signal of such a state. And here comes our first observation made in 2005. We reported on the ICAP in Innsbruck, 2006, on this observation. And you see a clear resonance. What is shown here is a measure for the three-body recombination rate. And this is just a scattering length, and at negative scattering length, so that's where these resonances are expected. At negative scattering length, we see a pronounced resonance when we produce a cold enough gas, 10 nanokelvin cesium gas. So this is the first observation of such an Efimov, triatomic Efimov resonance. Then similar resonances were observed in several, or already many other systems, like potassium-39 and fluorons, lithium-7 at Bar-Ilan and at Rice in Boulder, rubidium-85, and now we also have several observations on mixed species systems here of these resonances. But let me come back to the original picture here, and you may ask one immediate question, and this is, okay, where do I find this resonance? What is the position? What determines the position? We call it A minus. What determines the position of this resonance? Okay, and this means that it's a question in the field, it's the question of what is the three-body parameter. I have to explain what that means, the three-body parameter. Back to Efimov scenario, now you get these infinite series here of resonance points in this case. But what Efimov tells you, that there's this discrete scaling invariance, but at this point now short-range physics enters, and this is not contained in this picture. And so what is not known is the starting point. It's an additional parameter you need in this problem, and Efimov physics doesn't tell you anything about this. Okay, so this is the three-body parameter here. We can call this first resonance point we can use as a representation. That's what we do. We can alternatively, we can also consider the series here of energies, the point where the scattering length goes to infinity, and introduce a parameter kappa star, but that's just a different representation of the same thing. There's a universal relation. So let's stay in my talk, I will stay with these kind of parameters, the resonance points. Okay, so now in 2011, so what was the status there? So in theory, when everybody told us, yeah, it's a three-body parameter, it's a non-universal quantity. It comes from very short-range physics, affecting then the phase of the wave function, and this cannot be predicted for the system. So it's more or less random. Whenever you look at a resonance and you search for the resonance, it's just random where you find it within the Efimov period. Essentially unpredictable. Not very satisfactory. Okay, but we started a series of experiments on cesium again, and we exploited several, at least 4 different resonances in the same system, different resonances. And that was also the common belief in theory that a new resonance is a new game and it's not connected and it's again should be random. But what the experiments told us here are, data from 2 resonances, and it told us that this three-body parameter is essentially the same for all these resonances. And then we and others looked into other species, and they gave the same message. The same message when you normalize these A minus parameter length scale to the so-called van der Waals length, which characterizes the van der Waals interaction. So it's about this A minus parameter over the van der Waals length is about 9, and similar results have been obtained for lithium, potassium, and rubidium. So this cannot be an accident, and it is not an accident. So these results suggested a three-body parameter universality in atomic systems, and then several theoretical papers appeared and explained this kind of three-body parameter universality. Actually, what happens is that the van der Waals interaction with an r to the -6 potential is relatively steep. So it forms kind of a steep cliff, and this reflects the three-body wave function, and it never enters the region at really short range. So then it can also not sample short-range physics. But it's essentially determined by the van der Waals interaction. So what we learned is in atomic system, there's a new type of universality determined by the van der Waals, long-range van der Waals potential. If you express it in terms, so you can express this in terms of a length unit. This is the definition of the van der Waals length. And all observables are linked to these van der Waals length in the atomic systems. And no other short-range physics is relevant, in particular no genuine three-body forces here. And actually this is an interesting difference in atomic systems. This holds for atomic systems, but still for nuclear physics, it's a completely different situation because there really, you have to care about these short-range physics specific to atomic systems. Now, let me come back to this infinite ladder of states. So here's a logarithmic length scale. And you find these states with factor 22.7, 22.7, always the same. So this is the ideal picture. Now we know, expressed in terms of this minus parameter, there's a lowest state in the system, this one here. And we give it the index 0 because it's the, now we call it the Efimov ground state. But we know that this is linked to the van der Waals length. The van der Waals length is just a factor of 9 smaller. Okay, now what does it mean? Now we have to think again. So this Efimov picture of the infinite series only holds for a zero range interaction, a contact interaction. There's no effective range built in it. But now we see that the lowest state is somehow determined by this length parameter, which also characterizes the range of the potential. And it's only a factor of 9 away. So would you then expect that this follows an ideal scenario? Probably not. Probably the picture would look like this. There are some corrections here, particularly to the lowest state. So the question now is, what are these corrections, these finite range corrections? Are we still close to this 22.7 period, or does it completely destroy this picture? Another question is how can we address this experimentally? Okay, experimentally, so we have to observe this one, linked it to the van der Waals length. Can we observe the next one? This is the second Efimov resonance, the first excited state Efimov resonance. Will this be a factor of 22.7? Okay, we started experiments on that. We have to meet several challenges, big challenges. One thing, you have to control the scattering length on the level, I mean, the resonance is expected at minus 20,000 Bohr radii. This is a micrometer. Yeah? And we have to control this still on a very few percent level. This needs to be done. We need a very cold sample, a few nanokelvin sample in a non-condensed regime. But this will not be cold enough. So we will not be in the zero temperature limit. We have to understand finite temperature effects on our resonances. So we could meet all three challenges. The last one was not our merit, but that comes from Christophe Salomon's group in Paris. They looked at these boson gas at infinite scattering length and also developed a theoretical approach based on S-matrix, exact S-matrix solution. And so this kind of understanding of finite T effects is available. Experimentally, we had to work in a very weak trap with just 2.5 hertz trap frequency. It's a kind of hybrid trap, magnetic optic. And we have to control the scattering length, this amazing level, which works with what I call the amazing 800 Gauss Feshbach resonance in cesium. So this is a simplified diagram of the S-wave scattering length in cesium as a function of magnetic field. There are several broad S-wave resonances, and this one is the most extreme case, so for the experts of a broad or entrance channel dominated resonance. Thanks to long-standing also collaboration with Paul Julian, Jeremy Hudson on many, many measurements, we know the scattering properties extremely well. And we can tune into this regime and control the scattering lengths on the level of few 10,000 times the Bohr radius. So this is now how we meet this challenge. And before coming to the results, let me show two photos. One is this one here, taken now almost 5 years ago. This is Vitaly Efimov visiting Innsbruck in front of the cesium apparatus, somewhere here, where we did all the experiments. And so the second photo is the recent team photo, but with all the team members from the last few years. And at least 4 of them here are in the audience. And a subset of these persons here performed the experiment on the second Efimov resonance. Here's a subset, so Leonid and Bo in the lab, and we had theoretical support from Jeremy Hudson. And now I show the result. Okay, here we go. So this is now, again, recombination loss as a function of the inverse scattering length. So here, 0 is the pole of the resonance. 1 means on this scale it's 10,000 times the Bohr radius. And we see the peak we see somewhere here. Kind of naively, based on a factor of 22.7 and based on 0 temperature theory, we would expect the resonance to occur here. And you see it's clearly shifted. But what is the origin of the shift? Is it finite temperature or is it range corrections? Okay, fortunately we have this finite temperature model that we can apply. And if we say the resonance follows this factor here, and we just calculate from what we know from the first resonance, we just calculate 0 parameter fit. We calculate what we expect looks like this, almost on top of it. Okay, don't worry about this shoulder. This is higher order recombination. We understand this well. And this is three-body recombination here. Okay, but if you look now closely, very closely, then you notice there's still maybe a little shift. And we have to analyze this in more detail. More detail means, so we apply different fit models to understand where this position, this A- parameter of this resonance is. And we using different data sets, different fits to understand systematical problems. We came up then with the result. So minus 20,190 times the Bohr radius. We can relate this to the first resonance, which is known to this value. And then we can calculate the factor. And is it 22.7? It's 21.0. But with an error of 1.3, so we are 1.2 sigma away from this 22.7. Well, at least the picture doesn't break down completely. It's a small correction, if there is any. And if you look into theory, there's not much available. These range corrections you find in an early paper, something around 12. In a paper by Willi Zwerger's group, 17.1, and 20.7 in a recent paper by Zhuzhen Wang and Paul Julian, which comes very close. I don't want to comment on these things here. Maybe I'll discuss it in a little bit later slide. So we can test this now quite precisely, but now let me come back to the infinite ladder. What we measure is the first resonance and the second resonance, and we get these numbers here out for the ratios. And I think then, having this number, there's reason enough to believe and trust in theory, and here we can expect a factor of 22.7 with very, very small corrections. But now let me come back to this three-body parameter. This is a very important quantity to characterize this few-body system. And now we can express it actually in a different way. So we look into the n for large n limit, describing this. Before we used the position of this, but this is subject to range corrections. And this is the three-body parameter without these range corrections. And we suggest to use this parameter really as the best choice for the three-body physics. Okay, so this is about the cesium system. Now I want to switch to the fermions. I want to discuss a system which is very similar. How am I doing with time? Okay. So the three fermion system here, this is the three-boson system we investigated. And the system actually doesn't matter whether it's fermions. You just need three distinguishable particles. And if these three distinguishable particles, they all have large scattering length, then you find if the masses are equal, you find, again, the system follows the same scaling law, factor 22.7. And if all scattering lengths, these ones are equal, then it's formally equal to the three-boson system and should be the same situation. And the whole theory should, again, apply. And actually, lithium-6 is a very nice system, not only to study fermionic superfluidity, but also for few-body physics. We have in the high field region three overlapping broad Feshbach resonances, and you get this regime of three very large scattering lengths. And then what you get an Efimov state. The state is here, okay, and it has been observed about 5 years ago by Ken O'Hara's group also has enhanced three-body recombination. Okay, so we had Ken visiting us this spring for a couple of weeks, spending his sabbatical with us. And we looked again into his old data. The recombination resonance, these are experimental data from Ken. But now we used our new understanding, the finite temperature model. Dima Petrov extended it to actually to 3 different scattering lengths. And also there's now better scattering mapping from magnetic field to scattering length available. And we reanalyzed the data. And the quite amazing result, maybe to look at this number, we can now get the three-body parameter with a percent accuracy. I think this is really amazing. Before for the cesium it's 5%, here it's 1%. And now we can really provide accurate numbers also to test now these few body parameters. And it's very interesting that for cesium, this number, you compare these numbers, 6.89 and 8.8. So there seems to be a significant difference. And it's interesting now with a challenge to theorists to understand these numbers. I mean, now we are really at the stage that we can not only show qualitatively or half quantitatively some resonances, but we can really provide accurate numbers. We understand the systematics, and we can give an error bar on these numbers. It's now very interesting, I mean, to understand the three-body parameter question for different systems. It's almost the same for different systems, but there are some interesting deviations to understand this. System-dependent cesium-lithium, and in particular, what is also very important is the character of the Feshbach-resonance, whether it's broad, intermediate, or narrow. Cesium had the advantage, it's really in the extreme limit of a broad resonance. Lithium is also very broad, but if they get narrower, the situation becomes more complicated. Okay, so this is the conclusion of this part, but let me ask a final, if I have a few minutes left, a provocative question. So far, all what I showed was measuring losses, recombination losses. So you watch your system and it decays more or less. So is this only the physics of measuring losses? Fortunately, the answer I can give is no. And I just, in the remaining 3 minutes I have, rushed through an example. And what we are considering now is a mixture of 2 different fermions. So potassium-40 and lithium-6 that we have in the lab. Okay, and we consider this again with tunable interspecies interactions. We are in particular interested in the repulsive side of the resonance. Okay, and the three-body physics of this system, now you have, if you have a system like this, I mean the mass ratio of the heavy and light becomes very important. And these are identical fermions, and there is a p-wave barrier involved. But if your mass ratio is big enough, then it can overcome the effective attraction, can overcome the centrifugal barrier, you again get Efimov states. But this is the loss region. This is the region we don't want. The region below is, here it's known that there's another trimass state which does not have the Efimov properties. And our mass ratio is somewhere here, 6.7. But it's still pretty close to this 8.2 to the formation of the dimer. And this is a very important consequence. Now consider a process where a dimer scatters with a free atom. Okay, atom-dimer scattering. And these atom-dimer scattering, now let's look at the collision. Okay, when they approach each other, then the three-body nature becomes very important. And then it really becomes very important that we have a dimer state. Okay, that it's close to a trimass state. And if you are close to a state, then it creates a resonance. And actually, the prediction is, I cannot go through the theory, it creates resonance scattering mainly in the p-wave channel. Okay, so just one graph from theory. So this is the forward scattering amplitude. This is what you get with S waves only, near a Feshbach resonance. So this is the interspecies resonance. But close to the resonance, the higher partial waves, particularly the p wave, changes the sign of the interaction. There's a sign reversal. And this is an effect which is unique to the mass-imbalanced system. It does not happen in the mass-balanced case. So this is really a special few-body effect in the Fermi gas. Okay, so I cannot go through the experiment in detail. I just show the team photo, our theory collaborators. I rush to the next slides explaining the radio frequency spectroscopy. I just show an experimental result. So we measured, now we prepared an atom-dimer mixture, and we performed radio frequency spectroscopy on the free atoms and measure the shift. And then close to the resonance, you really see these expected shift, and that means the situation becomes attractive instead of repulsive. So the mass-balanced mixture would also always be repulsive. And this can be a strong shift, in particular if you get very close to the resonance. Okay, the conclusion from this part, in the mass-imbalanced system, a few-body effect can have fundamental changes, can fundamentally change the interaction properties, turning repulsion into attraction, and it's a few-body effect which is a lossless or nearly lossless effect. It's not an effect that manifests itself in losses, but really in shifts of the interaction energy. We are now working on the consequence of this effect on the many-body physics of the system. We have some hints that the ground state of the system on the repulsive side of the resonance is really completely different from the famous situation of a mass-balanced Fermi gas. Okay, and with that, I think I can conclude already, and thank you for your attention.
Thank you very much. Now it's time for discussions. Are there questions? So, yes, Bill. If there's a question from Bill first.
So this sign reversal from repulsion to attraction seems quite remarkable. That it happens only because of this mass imbalance. Do you have some kind of a hand-waving explanation that can give us a feeling for why this should happen?
I mean, you have to look into this in this interaction in a Born-Oppenheimer type picture. So when you have the two heavy ones and you have the light one around, and then it creates attraction in the attractive potential in the odd partial waves and repulsion in the even partial waves. And then you find, it's not very easy to understand that, but you find that then, particularly the P-wave channel, you get at the typical collision energies that we have in a nanokelvin, a 100 nanokelvin regime, you get huge phase shifts. And this is related to this, the trimer state is very close. It's like a resonant state which is a little bit above the threshold, and this introduces large phase shifts. And this modifies the whole picture. Actually, you have to sum up over all partial waves to get the picture correct. So S-wave alone is completely wrong in this situation, whereas it gives a good approximation for the balanced spin mixture.
Other questions? Yes, one there.
Yes, Rudy, you explained to us that at the end of the day, even if initially it was thought to be completely random, the three-body parameters scaled like a factor of 9 from the Van der Waals radius. And after explaining that, you showed results reinterpreted where the factor was different. So could you comment on that again?
Okay, so I mean, I think the zero-order picture, it is just a constant which is around 9 times the Van der Waals length. But this is not completely correct. There's still the wave function at short ranges samples something little bit. And there are some corrections to this. And this is something we don't understand completely. I mean, the theories show these variations. For example, the new paper by Jujun and Paul shows these variations. For cesium, for two resonances, for the two broadest resonances, there was a little 2-point-something sigma deviation of our numbers. And this seems to be real. There's something more, and it depends on the parameters of the Feshbach resonance. But this is something we definitely have to understand in more detail, these kind of corrections.
There is time for one last question. Yes, one there.
So you said right at the end that with this sort of new attractive interaction that you could have a different ground state and sort of new interactions. That sounds very interesting. Could that lead to some new state of matter, or what kind of interesting things could you expect?
So we have some hints in the experiment at the ground state. What happens in the balanced system is that you just form molecules. The ground state is a sample of dimers. But it seems that now with this attraction, if you get close to resonance, to pay some energy to dissociate a molecule, a dimer, but then you get the attraction with the rest of the sample, and you get this energy back. So closer to resonance, it seems that the ground state is a mixture of dimers and atoms. And it's an interesting question, what is the consequence now for different superfluid phases and polarized superfluids and these things? I think that's an interesting, very interesting question to pursue, and that's certainly what we're going to do in the future.
Okay, thank you. Let's thank Rudy again.